Okay, so what I want to do today, I'm going to continue chapter 4. We will be almost completing chapter 4, but we will have chance to do more examples on Thursday this week. Okay, so what I'm covering today is basically linear dielectrics, and then I'll talk about boundary conditions, in dielectric systems. Okay, so you guys watched my lecture, last Tuesday lecture? Yes, no? Yeah, I see the view counts. I see some of you did, many of you didn't. But good, excellent. Yeah, so I'm continuing the same discussion. So again, I want to start by drawing the diagram here. Imagine you have the electric field E naught in space, and imagine you put one piece of dielectric material in this electric field. Now we learn what happens is that this piece of dielectric gets polarized, right? So that means you can imagine these having many little small dipoles in this volume. And we talked about the polarization, and that's a vector that defines how the material is polarized. It has direction, it has a strength, and that depends on how much electric field we are exerting on this material. Okay, and then we said one question we are trying to answer is that what is the electric field? I call that E inside this material. Okay, so focusing on this dielectric, we have electric field. Okay, we have first of all a polarization. Okay, that is result of the electric field from outside, and then we have electric field inside this. And remember that the electric field that we get inside the dielectric is not equal to the electric field we have outside, okay? Most cases, what happens is that the electric field here inside is weaker than what we have outside, okay? And that's the effect of the dielectric, okay? So from this P and E, we defined a vector, and we call that electric displacement, which is epsilon naught times E plus polarization, okay? And we said this D, electric displacement, is very useful, especially for the cases that you want to, you have a charge distribution, and from the charge distribution, you are trying to find electric field. In the presence of dielectric material, it's hard to directly go from any charge distribution and calculate E, because any electric field is a result of two combined forces. One is the polarization, one is the electric field from outside. Okay, so typically in a lot of problems and in a couple of examples that we want to do today, we have a charge distribution and we want to find the electric field. But instead of going directly and finding electric field, what we do is that from charge distribution, we find D, which is electric displacement, okay? And from D, we can calculate electric field as well as the polarization vector P. Okay, so in many cases, the electric field and polarization are also correlated with each other. They are linearly dependent on each other. That happens for a lot of materials when the electric field exerted on this is not too strong. Okay, and they are called linear dielectrics. Okay, so if we can correlate E and P in an equation like this, we basically can end up having just one unknown, and that can be the electric field, and we can calculate Okay, so what we're going to do today, we're going to make assumption that electric field and polarization are linearly related to each other. And if that is the case, we can always start from charge distribution, calculate electric displacement, and from that we can calculate both E and P. If we don't make that assumption that they are linearly correlated with each other, then we will end up having two unknowns and one known, and it's hard to move from electric displacement to electric field and polarization. Okay, so now I'm going to look at how P and E can be related to each other and what are the equations that connects these two together. Okay, so for that I'm going to get rid of this part. So the relation between P and electric field polarization, if we say it's linearly proportional to electric field, we mean something like this. Whatever electric field we have polarization, which is, let's say, alpha times E. Okay, and for alpha, the convention is that we define it in terms of epsilon 0 times chi E. Okay, and epsilon 0 is the usual factor. It's permittivity of the vacuum, permittivity of the free space, and chi is defined as electric susceptibility for this material. Okay, so any dielectric material, there is a definition, there is an electric susceptibility associated with that, and that can be measured and so on. So chi naught is electric susceptibility. Okay, and if P and E related like this, we can rewrite D all in terms of the epsilon 0 E, and then we can sub P back here. Everything is going to be proportional to electric. Okay, so D, if I sub this back into that equation, is epsilon naught E plus epsilon naught chi E times E, which is basically epsilon naught 1 plus chi E times E. Okay, so, and if you write it in a short way, we can define epsilon naught plus chi E as epsilon, and this will be the electric permittivity of this dielectric. Okay, or if we write it in short term, D is epsilon times E. Okay, so if we find electric displacement that's linearly proportional to electric field as well. Okay, so with this set of equations, in a lot of cases, we can easily move on from whatever charge distribution we have. We can calculate D and we can calculate E as well. Okay, and I hope you remember from last Tuesday lecture that D follows the Gauss law if we only include the free charge distributions in the problem. Okay, that means D can be calculated based on the free charge distribution based on the Gauss law. That means the integral form is like this: D dot dA equals Q enclosed. I'm going to call that the QF because we only look at the free charges and not bound charges, which are result of the polarization. And the differential form of this is divergence of D is rho F. Okay, so D is related to charge distribution through these two equations. These are basically same as Gauss law, but for the electric displacement. Sounds good so far? Any question?
What is the x looking variable?
This X is chi, is a Greek letter chi, and that is electric susceptibility.
Okay.
Sounds good. So I want to go back to the example that we did last Tuesday. Okay, I want to go back to that example. And what we did last Tuesday was from that charge sphere, we calculated electric displacement. Now I want to make the assumption that the dielectric that is encapsulating the charge sphere is a linear dielectric. And from that I can calculate electric field as well as the electric polarization. Okay. So let me get rid of this. And by the way, what I'm doing now is the example 4.5 in chapter 4. So write here example 4.5. And the example is that you have one charged sphere that carries the charge of Q. Okay. The radius of the sphere, let's assume the radius is A. And the whole sphere is covered by a dielectric material up to radius B. Okay. Meaning that, let me choose a different color. Okay, so this is the radius. So the area between is covered by a dielectric material. The question is asking what is the electric field inside the dielectric and what is the electric field outside the dielectric. Okay, so here we are asking what is E, and here we are asking what is E as well. Okay. So if there was no dielectric, okay, this was an easy problem. You know that electric field at any point here could have been calculated, and the E electric field is 1 over 4 pi epsilon 0 Q, the charge on the sphere divided by R squared times R hat. And that is electric field at any point outside this sphere if there was no dielectric material. Okay. Now we have this dielectric. We want to see what is the effect of this. How does it change the electric field inside the dielectric material, and what is the electric field outside? Okay. So the way to do this is we use the Gauss law because of the symmetry of the problem. We have a spherical symmetry here. Okay. We use the Gauss law, but we cannot directly use the Gauss law on electric field because of the complexity from the dielectric material. But what we can do, which is as easy as that, is using the electric displacement. And then here, the free charge, the QF, is basically the same charge that we have on the sphere Q. And we can ignore any charge, bound charge created by the polarization in the dielectric material. Okay. And what that means is that we can calculate D at any point, okay, outside this sphere. Okay. Let's do that. I choose a Gaussian surface, which is basically just one sphere. This can be inside the dielectric material or outside, doesn't really matter, because as long as you are focusing on D, you don't even need to care about the dielectric material. Okay, so here the integral of D dot dA should be equal to Q enclosed free, and D dot dA, because of the symmetry, I can say it's magnitude of D times 4 pi R squared, and R is the radius of the Gaussian surface that I am considering. Okay, so the red one here is a Gaussian surface. Sounds good. d times 4 pi r square is this integral, and then q free is the q we have. Okay, so d is basically 1 over 4 pi times q over r square. Okay, and this is the d in terms of the magnitude of d. D basically is a vector, and through the symmetry of the problem, we can easily conclude that d should be in the direction of r, and this is the electric displacement. Okay, this is electric displacement inside and outside of the dielectric material as a function of r, distance to the center of the sphere. So here, this is correct for inside and outside. And that's important, okay? And that's what makes the electric displacement something very useful, because you can totally ignore whatever dielectric material you have. D doesn't care about that, and you can calculate D based on this Gauss law. Sounds good so far? Is it more or less clear? Okay, and now as soon as you have D, you can move on and calculate electric field. Okay, and then I would say it's easier to look inside and outside separately, because inside the dielectric material, we have dielectric constant, which is different from that of outside. Okay, so what I want to do is that I want to first look and see what is outside, okay? And by outside, I mean R being greater than B, okay? So outside, what we have is we have free space. The permittivity is epsilon 0. Okay, and if you look at this equation, this is always correct. D is epsilon times E. And in the free space, permittivity epsilon is equal to epsilon 0. So this equation is D equals epsilon 0 times E. Okay, and so electric field is simply D divided by epsilon 0. We already calculated D here. We just need to divide that by epsilon 0, and we get what we get is electric field E is 1 over 4 pi epsilon 0 Q over R squares times R hat. Sounds good? And this is exactly the kind of electric field we expect to get when we have a charge of Q right here, okay, and without any dielectric. So outside the dielectric material, we get an electric field which seems to be independent of the dielectric material we have, okay? So encapsulating this charge sphere in this dielectric material does not affect the electric field outside the dielectric. Okay, now let's look at the electric field inside this dielectric and see what we get. Okay, let me erase this. And when I say inside, I mean R being greater than A but smaller than B. Okay, this puts us inside the dielectric material. Okay, so here we already have D in terms of R, but then we know that the electric permittivity is epsilon, which is epsilon 0 times 1 plus chi E. Okay, that's the permittivity we have. The electric field is epsilon times E. That means E should be D divided by epsilon, which is equal to D divided by epsilon 0, 1 plus chi E. Okay. The electric displacement, we already calculated that here. So D becomes 1 over 4 pi epsilon 0, which is this factor, times Q. Well, of course, we have that 1 over times 1 over 1 plus chi e times Q over R square times R hat. Okay. So this is the electric field that we get. Oh, sorry, this is E. This is the electric field that we get inside the dielectric material. Okay. So what would have been the electric field if there was no dielectric material here? Okay, we would have the same term here, but not having this. Okay, so this is basically the effect of the dielectric material. So can you guys tell me this ratio, 1 over 1 plus chi, is it greater than 1 or smaller than 1? Chi is always a positive number, it's never negative. Okay, so this ratio is something smaller than 1. Okay, so if you look at this electric field, if you compare to the case that there was no dielectric material here, we find that electric field here reduces as an effect of the dielectric material. Okay, so if you encapsulate this charged sphere inside this dielectric, you get a smaller electric field inside here, but the electric field outside remains intact. It's not affected by that dielectric. Sounds good? So what we did so far, we calculated the electric displacement, which is correct for inside and outside of the dielectric material everywhere, okay, everywhere outside the charge sphere. And then to calculate electric field, we first focused on outside and then we looked at inside. Why did we separate them? Because we are looking at two different regions with different permittivity. Outside permittivity is epsilon naught. Inside permittivity is epsilon, which is epsilon naught times 1 plus chi e. Okay. What we find for electric field outside, we find it's exactly the same electric field that one charge sphere creates in free space, regardless of the presence of this dielectric. But when we look at the electric field inside, we find that we have this term, which tells us that we have a reduced electric field inside the dielectric. Sounds good? So again, what we did was we moved from charge distribution to electric displacement, and from that we moved on to electric field at different parts of the space. Any questions so far?
So outside, it's always epsilon naught, right?
Outside, because we do not have any dielectric, we are in free space, so it's always epsilon naught, yes.
And R is the distance to the Gaussian surface, right?
Is the distance of the Gaussian surface to the center of the sphere. So this could be inside or could be outside the dielectric material.
Okay, thank you.
Sounds good? So now we have D, we have E as well. From these, we can calculate the polarization inside the dielectric material, right? We can calculate polarization inside the dielectric material, and from that, we can see what kind of charge accumulation, bond charge, we have on the surface or inside the dielectric, okay? So in order to calculate polarization, we can start from electric fields that we calculated, okay? So outside, there is of course no polarization because there's no dielectric. So I want to say, no, for polarization, I want to use blue. So outside, there's absolutely no polarization, there's no dielectric, so P is 0. But inside, we have polarization, and that should be equal to epsilon naught chi e times electric field. Okay, and that is the electric field we have. So I'm going to look at the polarization, and then I'm going to look at what kind of surface charge and volume charge we have due to the polarization. Okay, so let me get rid of this D because we don't need to use that anymore. Okay, so what I'm doing here is for this part inside the dielectric. Okay, that's where we have the polarization. P is equal to epsilon naught chi E times E. So I'm going to take the whole thing here and multiply that by epsilon naught times chi E. Epsilon naught cancels this, and chi E multiplies here. So we get 1 over 4 pi times chi E over 1 plus chi E times Q over R squared times R hat. Okay, and that's the type of polarization that we have inside. Okay, so if the charge of Q is something positive, okay, so let me mention something like plus Q here, then the direction of the polarization is in the R hat direction. That means it's away from the center. Okay, so if Q is positive, the direction of the polarization is in the radial direction, and it looks like this. It's moving outward. Okay, so as soon as we know polarization, we can look at what is the bound charge density and what is the surface bound charge density. If you remember, rho B, the volume density of bound charges, was negative divergence of P. Okay, so if you look at this one, P is proportional to 1 over R squared times R hat. Divergence of that function is always 0 except right at the origin. Origin, we don't care about that because the dielectric material is not present at the origin. So there is no volume charge accumulation of the bound charges. Okay, but what else we have is accumulation of surface charges on the outer surface and on the inner surface here. Okay, and sigma B, the general equation, the surface bound charge density is P times n hat. N hat is the unit vector perpendicular to the surface. Okay, so if we look at the outer surface, sigma B should be P at B. Okay, P at right radius here. I write that as P at B times n hat here is actually R hat. Okay, the unit vector perpendicular to the surface outward is R hat. So we have PB dot R hat. And if we substitute B as a radius here, okay, and we do the dot product by R hat, we have R hat dot R hat here, that just becomes 1. So what we get as surface charge density, sigma B, at the other surface is 1 over 4 pi times chi E divided by 1 plus chi E, okay, times Q over B squared. Is it positive or negative? That depends on the sign of Q. But if Q is a positive charge on this sphere, the charge induced on the other surface becomes positive too. Okay, and I'm going to draw a diagram to make sense of this. Okay, if we look at the charge accumulation on the inner surface, sigma A, which is inner surface, sigma B, the bound charge on the inner surface, we have exactly the same thing, except that we are looking at the surface at the radius R, at the radius A, and the normal component, normal vector to the surface is actually pointing inward, okay? And that is actually negative R hat, okay? because this is the surface, this is the volume of the dielectric, and we are looking at the surface that is pointing inward. Okay. If we look at that, then sigma b, the bound charge accumulation on the inner surface, becomes very similar thing, except that you have a negative sign and the radius here is I. So we get negative of 1 over 4 pi chi e 1 plus chi e times q times a squared. Okay, so this is the surface charge density on the inner surface. Okay, so is it positive or negative? Of course, it depends on the charge of Q, but if Q is positive, we're going to have negative charge accumulation here. Okay, so I hope you remember the discussion we had on how the polarization can lead to accumulation of charges on the surface and also volume charge. Okay, we discussed last Tuesday. I'm gonna repeat that discussion for this specific problem and try to explain qualitatively why do we expect positive charge distribution outside and negative charge distribution on the inner surface. Okay, so let me get rid of this part. Okay. I want to draw part of this sphere in a magnified way. Doesn't look good. Okay, so imagine this is where we have this sphere that carrying the charge Q, and this is the dielectric material we have. Let's make the assumption that Q is positive, so we have positive Q here. Okay, and we said if Q is positive, the polarization is a vector pointing in the r hat direction. Okay, so the direction of polarization is this. And what it means is that it means we have dipoles inside this dielectric that align in this direction, positive and negative. Okay, and that means we have many, many of these dipoles. Okay, so if you follow these dipoles and you imagine if you have many of them, okay, you have all these positive side pointing outward and negative sides pointing inside. Okay, and what you have, if you have a series of them on the inner surface, you have accumulation of only negative charges here, and the other surface, you have accumulation of the positive side of the dipoles. Okay, so if you only focus on the surface here, you see all these positive charges. If you focus on the surface inside, you see the negative charges. Okay, and that's why we expect that if Q is positive, the sigma B, the induced charge on the other surface, be positive, and on the inner surface, be negative. Sounds good? I hope it gives you some insight how polarization is creating surface charges, bond charges.
So from A to B, the material is like all within that space, right?
The material is always in this space, and the material is polarized, okay? And this is the polarization vector that we have for any point in this material. If Q is positive, the direction of the polarization is outward. That means all the positive ends of the dipoles are this side, and negative sides are inside, okay? So inside the material, the positive and negative charges cancel out each other. There's no net charge here in the middle. But if we only focus on the surface, we have accumulation of positive charges on the outer surface and accumulation of negative charges on the inner surface. Sounds good? Any question? And it's interesting that the polarization and effect of the bond charges is such that the electric field inside reduces, okay? So if the charge is positive here, the surface charges negative to positive create an electric field which is pointing this way, right? So this is the electric field created by the polarization, okay? The electric field due to charge Q is actually this way, okay? So the effect of polarization is such that it balances partly the electric field created by this Q, which is a free charge, okay? And this is interesting because if you look at capacitors, people use dielectric material inside the capacitors because people want to reduce the electric field and reduce the voltage difference on two sides of the capacitor, and that increases the capacitance, okay? So the next example I want to do is a parallel plate capacitor, very similar to what we did before, except that now we put a dielectric material inside, and we want to look at how that dielectric material enhances the capacitance, okay? So let me raise this, and we're gonna do next example. Any more question on this? Okay, so if there's no question, let's get rid of this. Okay, so next example is example 4.6. Okay, and here we have a parallel plate capacitor which is filled by a dielectric material. That means between the plates, we have the dielectric material. And this dielectric material has the permittivity of epsilon, which is epsilon naught times 1 plus chi e. And that already means that epsilon, like any dielectric, is greater than epsilon naught. Okay, so now I want to look at the capacitance of this capacitor and compare it with the case that there is no dielectric material between the plates. Okay. Okay. So imagine the distance is d between the plates, and imagine the area of each plate is A. Okay, so I hope you remember that the capacitance is Q divided by delta V. Okay, so I want to compare two cases, one of them with no dielectric material, the other case with dielectric material. So I want to say C naught is a case that we do not have any dielectric. Okay, so if we do not have any dielectric, the capacitance is Q by delta V, and Q is technically the sigma, the charge on the plates, times the area of the plates, And delta V that we get is E electric field times D. The electric field created between the two plates is sigma divided by epsilon 0. This is the case for inside the dielectric, inside the capacitor where we have positive and negative plates. So the capacitance becomes sigma A divided by sigma D epsilon 0. Sigma is cancelled out by the both sides, and we get, let me get rid of this, and we find that the C naught capacitance of this capacitor being epsilon naught A divided by D. Okay, so this is the capacitance when there is no dielectric involved here. If we repeat the same calculation where we have the dielectric material, we have C, which is Q divided by delta V. Q is the same thing, sigma times A, but then we have delta V that is created by the electric field here, E times D. Now this electric field is different because of the effect of the dielectric. Okay, so if we want to calculate E, we should first calculate D, and then from D we can calculate E. Okay, and if we look at these parallel plates, we can do exactly the same type of calculation we used to do in terms of choosing Gaussian surface. The electric displacement becomes sigma, okay, and the electric field inside this dielectric, E is D divided by epsilon, okay. So we have sigma divided by epsilon is the electric field here, which is equal to sigma times epsilon 0 times 1 plus chi E, okay. And this term 1 plus chi E in the denominator already tells us that the electric field we are getting here after adding dielectric is smaller than the electric field we used to get here in this case without dielectric material. Okay, so combining these two, if I use this electric field here, the capacitance becomes epsilon times A divided by D, which is epsilon naught times A divided by D times 1 plus chi E. Again, 1 plus chi E is a number greater than 1. That means the capacitance, in the case that we include dielectric, becomes bigger than the capacitance without the dielectric. Okay, why does that happen? Because putting this dielectric reduces the electric field, and that reduces the voltage difference between the two plates of the capacitor. Okay, that itself increases the capacitance. And most of the capacitors you find out there are always some dielectric material between the plates. Sounds good? In the problem set that I assigned to you, there are a number of cases, actually two problems, there are two different cases that you have different dielectric materials, okay? In one of them, you have two different slabs on top of each other, and you put that between the plates. And in the other case, you have dielectric material filling only half of the space between the plates, okay? And those are interesting because you have one capacitor, but basically in terms of the calculation of the delta V and electric field, you have a couple of capacitors connected to each other in series and in parallel, okay? I hope you will enjoy working on those two problems. Any question on this? Is this more or less clear what's happening here? in terms of the kind of electric field we get when there's no dielectric, and the electric field that we get when there is dielectric. Okay, I hope you will get a chance to work on these examples on your own, and then it becomes clear. Basically, it's very similar to the previous problems we had with a tiny bit of difference. That is the result of the dielectric. Good. If there's no question on this, I want to move on to the next topic, which is boundary conditions when we have dielectrics. Okay, and that follows the same discussion we had for boundary conditions in terms of the discontinuity in the perpendicular component of the electric field across the surface and continuity of the tangential components. Now we're going to look at the cases that we have a charged surface, and on both sides, instead of free space, we have dielectric materials. Okay, so let me clear this. So boundary conditions, we already talked about the cases that we have a surface carrying the charge sigma, and we looked at the electric field above. And the electric field below the surface. Okay, and we said because of this charged surface, the vertical component of the electric field is not the same on the both sides. Okay, and when we looked at the E, the vertical component above, and electric field, the vertical component below the surface, we said that there should be discontinuity. Epsilon naught times E above minus epsilon naught times E below should be equal to sigma. Okay, and at the same time, we said the horizontal component, the parallel component of the electric field E above should be equal to the parallel component of the electric field below. Okay, now we want to look at the situation that we do not have free space up there and not free space down here. We have some dielectric material. Okay, so I'm putting a blue shade here, meaning that we have one dielectric material here and a different dielectric material below here. Okay, and here we have epsilon. I call that epsilon above. We have dielectric material could be different below and epsilon below. These are the true permittivity associated with the material above and material below the surface. Still, we have the charged surface here, okay? And now that we have these dielectrics and we have bound charges created by those dielectrics, I choose to call sigma, the charged surface that we had, sigma F, just to emphasize that this is a free charge density independent of any induced charge on the surface of the dielectrics. Sounds good? So now the question is how these two equations are modified when we have these dielectric materials. And if you have dielectric material, there is always a chance of certain accumulation of charges on the boundaries as well. Okay, so if you remember, we came up with these two equations, the top one, we came up with these by following the Gauss law, E dot dA which is equal to Q enclosed on a box that covers this boundary. Okay, we can do the same thing if we have dielectric material, but then instead of E, the easiest way is following the electric displacement. Okay, so following this, we came up with this equation for the vertical component, for the perpendicular component of the electric field. Now with dielectric material, what I want to do is that I want to repeat the same thing and focus on the electric displacement. Okay, so here d dot dA, we know it's equal to enclosed charge, free enclosed charge. Okay, so from this one, I can easily come up to the conclusion just by the virtue of comparing the equations, saying that the perpendicular components of the electric displacement above minus the perpendicular component of the electric field below should be equal to sigma F. Okay, so here we had epsilon naught in the equation. Okay, here we do not have for the electric displacement here. Okay, so following this, we came up with this. Following this, we can come up with this. Sounds good? And then what is D above is basically epsilon above times E above. So the first term becomes the permittivity of the dielectric above the surface times electric field above the surface. And then D below is permittivity below the surface times electric field below the surface. That should be equal to sigma F. Okay, so this equation already tells us what should be the discontinuity in the normal components of the electric field. Okay, this has very similar shape as what we had before, with the difference that instead of epsilon naught and epsilon naught, we have the epsilon of the above and epsilon of the below dielectric material. Sounds good? And then the horizontal component of the electric field is going to be exactly the same. There is never discontinuity in the parallel component of the electric field, so E parallel above is always equal to E parallel below. Okay, sounds good? So this is kind of the more general form of this equation where we have dielectric material. If we remove this dielectric material, you're basically replacing the E above with epsilon naught and E below by epsilon naught. Okay, so these two equations have the same nature. Okay, this is just more general because it includes any type of material with any level of permittivity. Sounds good? So we have 15 minutes. I can do one example, and that is the example where we put a sphere inside electric material. But before that, tell me if you have any question on this. And if it's not clear, ask me. The class is a little too quiet today.
For the drawing, so the material is on both top and the bottom?
Yes, you can have one type of dielectric material above and different type below, okay? And what defines what material you have is this permittivity. And E above and E below, I made assumption they are different. It could be the same, but I made assumption that they are different.
Okay.
So I just want to understand that all of this, thanks to the similarities between using the Gauss's law.
Yes. Okay. So basically, as soon as you have dielectric material, if you want to use the Gauss law, you should move on to electric displacement because that makes it easy for you. And this is always correct. Okay, this is pretty general and this is always correct. the same way that usual Gauss law was correct for the case that there was no dielectric material. Okay, so I moved from this one to this one because now I have dielectric material. And the rest is just mathematics. And what type of equation you get out of this is very similar to the equation that you get for usual Gauss law.
So it's always approaching the displacement using any Gaussian surface if there's good symmetry and everything else goes through simple arithmetic.
Yes, yes. So if you see a problem that you have dielectric in that, just be sure that you need to use Gauss law for electric displacement. Okay, and if you have good symmetry from the charge distribution, you can calculate D. Moving from D to E for linear dielectric is just one step. Okay, just divide D by epsilon, and then you get electric field. Yeah, things like this, you gotta do examples a couple of times, and then you will see it's easier than what it looks from beginning. Okay, so I very carefully chose the problem set that I assigned. So from each problem, you learn something. Okay, if you understand all those problem sets that I assigned, things like this becomes easy for you. And the exam will be easy for you too, okay?
Yeah, I'm just impressed by how powerful Gauss's law is.
Oh, it is impressive how powerful that is. I mean, if there's symmetry, of course, you can use the integral form of the Gauss law. But even if there is no symmetry for any sort of complicated geometry, you can always use the differential form in a computational program. And that just works very surprisingly well. Okay, and the type of differential equation we get from the differential form of the Gauss law is interesting because with computational methods, you can always push it to the limit and calculate that with very good precision. Professional people use that all day long when they want to calculate the electric field from waves and everything else. The electric has to be the difference of the electric fields caused by the dielectric. Yes, the electric fields are discontinuous. Okay, first of all, because of this free charge, because the surface is charged. Okay, and second, because of the difference between the dielectric permittivity of the two materials. If you really have two different materials with different permittivity, even if you set sigma f equals 0, you will get different electric fields on both sides. Sounds good? Okay, so I want to start the next example. Okay, I'm not sure if I finished that, but it's good to start it, and I lay down the basics. And with that, we're almost done with the chapter 4. Still, I need Thursday to finish it, but we're almost done. Okay, so I want to move on. It's going to be example 4.7. That we have electric field and we are putting a sphere, dielectric sphere, inside that electric field. The example is very similar to the other case that we put a conductive sphere in an electric field. Here we have a dielectric sphere. So imagine you have a uniform electric field in a space, and then you put dielectric sphere inside this electric field, okay? And what happens is that you get electric field lines curved a little bit, and of course other lines curved like this. And then the question is, what kind of electric field we get inside? And I'm already drawing the surprising answer that the electric field inside becomes uniform. Okay, so electric field outside is E naught. Okay, if we make the assumption that z direction is above, E naught is basically a constant, E naught times z hat, or in the E naught times z hat. And then I'm going to use a spherical coordinates, assuming that the origin is here, the radius of the sphere is r, okay? And I'm going to look at the potential. So what I want to do is that I want to start with potential. I want to first look at the boundary conditions, what type of boundary conditions we have, and then I want to look at the general solution for the spherical coordinate that we have in terms of the Legendre polynomials and whatnot, and then I want to find the potential. Okay, to do that, I want to separate the potential that we can get inside and outside. One of them I'm going to call that V in, which is as a function of r and theta. These are the coordinates, the parameters of the spherical coordinates. I don't need to use phi because of the spherical symmetry. Okay, so what is important is r and theta. R is the distance to the center, and theta is the polar angle. And so we have V in and V out of r theta. Okay, and the first one refers to potential inside the sphere. The second one refers to potential outside the sphere. Okay, and these two need to be connected through the boundary condition that we have here. Okay, so I'm going to say what are the boundary conditions. So number one, the potential needs to be continuous when we cross the surface of the dielectric material. There's never discontinuity in the electric potential. Okay, so number one, V in r theta should be equal to V out r theta. I use capital R because I want to mention that R is on the surface of the dielectric sphere. Okay, so this is a condition of the continuity of the electric potential on the surface of the dielectric. Number two is the discontinuity of the electric field. Okay, so following the previous example we have dielectric material here, which permittivity of the epsilon. We have free space with permittivity of epsilon naught, two different levels of permittivity. So the normal component of the electric field can be discontinuous. Even though there is no free charge, there is no sigma f on the surface here. So I mentioned that here, sigma f is basically 0. But because of the two levels of permittivity, we can have discontinuity of the electric field. An equation for that is epsilon, which refers to permittivity inside, times E perpendicular inside should be equal to epsilon 0 times E perpendicular outside. Okay, and this happens right at the boundary where R is equal to R. Okay, so what is E perpendicular inside? We can write that in terms of the derivative of the potential with respect to radius. Okay, and that becomes dV in dr. Okay, and this one is going to be dV out dr. Okay, so this is the second boundary condition on the surface of the dielectric material. Okay, the first one is continuity of the electric potential. The second one is discontinuity of the electric field. Okay, the boundary condition number 3 is for the case that we are way far from the surface. It's where R is much greater than R. We are close to infinity. The way the electric field and electric potential should behave should be equal to the behavior of this electric field, because we know that the electric sphere is not going to put is going to make much difference at positions that we are far from it. Okay, so if we are so far from this, the potential created by this is always E naught times Z. So potential at far distances is this, by the way, negative of this, which is in polar coordinates is negative of E naught R cosine theta. Okay, so boundary condition number 3 is at R much greater than R, V, which is basically the potential out, V out of R theta should be negative of E naught R cosine theta. Okay, so these are the 3 boundary conditions that we have, and we need to find V in and V out based on these 3 boundary conditions. The starting point for V in and V out is the general form of the potential expanded in terms of the Legendre polynomials and the boundary conditions that we have. So A L r to the power of L plus BL over r to the power of L plus 1 is a radial component. This is what we had in the chapter that we discussed separation of variables, times PL of cosine theta. Of course, we're going to look at a series made by this. Okay, so this is the general solution result of the separation of variable. This is the function, only function of r, and this is the function, only function of theta. And summation of that is the general solution we had. Okay, so for V in and V out, we are looking at 2 different cases. V in includes the radius when radius goes to 0. So for V in, we need to completely get rid of this term, otherwise the potential blows up. For outside, we should get rid of completely this term, r to the L, because that makes the potential blow up at infinity. Okay, so this is gonna be our starting point for V in and V out that we're gonna solve subject to these boundary conditions. Okay, so here I just laid down what problems we have, what boundary condition we have, and what general solution to start with we have for V in and V out. I'm gonna stop here because time's up. On Thursday, I'm gonna start from here and finish this example. Sounds good? So you guys, I suggest you start working on the homework problems right away, okay, and try to do them, understand them. It's okay to talk to each other, but it's not okay to copy paste and not understand what you're submitting, okay? And start early and prepare for the quiz, and that's already gonna prepare you for the final exam as well, okay? Any question? Good.
I do have one question actually about.
Can you speak a little louder?
I do have one question about the midterm. Are we going to be able to get our like basically what we did wrong on our
Yes, send me an email, okay? It was crazy grading this because I had to look, I didn't have the paper, I was looking at the monitor and trying to grade there. Send me an email, I send a PDF of your exam, and then we can discuss on that.
Thank you.
Yeah. If you are not sure your grade is okay, definitely do that so that we can make a discussion, and if needed, we can adjust the grade. Send me email. Excellent. Okay, you guys enjoy the rest of your day, work hard, and see you on Thursday morning.
Thank you.
Thank you.
Bye.
Thank you.